Pluto is a faraway and perplexing minor planet, a planet that was once thought to be a part of the planetary group's planetary family. However, recent alarming announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an incredible revelation. They suggested that this chill world is on a course of influence with Neptune. Yet, how could this happen? And what might be the results of such a significant event? Are we seeing an intriguing cosmic eccentricity, or is there an additional factor in this approaching limitless effect? Join us as we examine the potential outcomes of a collision between Pluto and Neptune. Pluto, a past planet that shrank to the size of a dwarf planet, is somewhat a mystery because of its odd orbit, and it remains a subject of interest and study in the astronomy community. As indicated by recent expectations by leading specialists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which could represent a critical risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires an unbelievable 248 years to finish a single orbit, meaning that it hasn't even completed one full revolution since its discovery in 1930. However, the interest doesn't stop there. Pluto's orbit is marked by its astonishingly curved shape that deviates altogether from the almost round orbits of the significant planets. What makes Pluto's orbit even more amazing is its inclination of 17 to the ecliptic plane. The course Pluto follows is much steeper than those of other planets. One of Pluto's most intriguing features is its orbit's crossing point with Neptune's. For something like 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what we'd expect from their positions in the planetary system. This prompts the natural question, why hasn't Pluto collided with Neptune? The response lies in the gravitational effects of other worlds. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unique orbit. Unlike other planets, whose orbits lie mostly close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and curved shape. The realization that Pluto's orbit does indeed cross Neptune's made the mystery even more complex. Pluto's steadfast orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies, like Pluto, Neptune, and the Sun, move and affect each other through their gravity. Pluto's orbit is, in fact, turbulent. Minor departures from the initial conditions can lead to significant variations across millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over especially long time frames that keep tumult under control. The most recent simulations have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These factors are essential in maintaining the order and consistency in the motions of the universe. Without these factors, our local planetary system would be a place of much more unrest and unpredictability. Pluto's orbit is a remarkable illustration of celestial mechanics at play, displaying both stability and chaos in our local system of planets. The unique characteristics of its orbit, influenced by the gravitational forces of nearby planets, especially Neptune, highlight the intricate and dynamic nature of space. Predicting major events, particularly when they involve turbulent orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems indicates that long-term forecasts are often filled with skepticism. While simulations are an effective tool for understanding and predicting the future behavior of celestial bodies, they also draw attention to the limitations of our predictive abilities. So, why are prominent astrophysicists only now raising concerns about a potential crash between Neptune and Pluto? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concerns about the possibility of Pluto colliding with Neptune. If Pluto and Neptune were to collide, it would be a captivating and devastating event in our neighborhood planetary system. The impact would release an immense amount of energy, probably breaking Pluto, given its smaller size and icy composition. Debris from the collision could scatter across the planetary system, which could put the moons of other planets in danger. For Neptune, a collision of this kind could alter its current setting and possibly its orbit based on the particulars of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the discussion as well. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide useful insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto can yield important insights for future space missions. This knowledge can help in navigating the planetary system more efficiently, predicting potential hazards, and even planning missions to the outer reaches of our solar system and further. The knowledge gained from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. Regarding the physics of planets, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, rely on fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could possibly have a connection to string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, aim to explain the basic elements of matter and forces in the universe. The impact could result in extreme conditions of energy and gravity, possibly creating circumstances where predictions made by string theory could become detectable. For example, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme circumstances, a crucial part of the fascination with string theory. While the direct effect on Earth would be negligible due to our distance from the outer planets, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental description of the universe's nature by string theory and other areas of physics theories. Pluto's confounding dance around the Sun continues to captivate researchers and enthusiasts alike, providing a window into the complexities of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and redefined our understanding of planetary bodies, recent discoveries about its orbit have reignited interest in its role within the local planetary system. Neil deGrasse Tyson and Michio Kaku, two distinguished astronomical voices, have raised concerns about a potential crash between Pluto and Neptune, shedding light on the complex dynamics at play in our cosmic community. Their warnings emphasize the significance of comprehending the forces of interactions and orbital mechanics that govern celestial bodies' movements. The orbit of Pluto, distinguished by its unpredictability and steep inclination, defies traditional assumptions and challenges our understanding of planetary movement. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, intersecting with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in determining the orbit of Pluto and preserving its stability over hundreds of years. Despite the turbulent nature of its path, numeric simulations and theoretical models play a vital role in predicting the future behaviors of celestial bodies and understanding the complex interactions between planets. These simulations show that, while Pluto's orbit is turbulent, it remains relatively stable within the broader structure of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and intricacies in planetary dynamics. While such an event remains speculative and extremely unlikely in the near term, the gravitational dance between Pluto and Neptune underscores the fragile balance of forces that govern celestial bodies inside our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future missions of space exploration. The New Horizons spacecraft, launched by NASA in 2006, provided exceptional images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaboration necessary for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outermost parts of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, furthering our understanding of planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the classification criteria for celestial bodies within the solar system. The controversy over planetary categorization reflects broader questions about scientific classification systems and the evolving nature of astronomical knowledge. While Pluto meets some criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These understandings are essential for developing theories about the origins of our solar system and understanding the processes that shape planets over billions of years. Pluto's discoveries and subsequent research have contributed to our understanding of planetary migration and the development of the Kuiper Belt, a region beyond Neptune populated by small, icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system. The gravitational influence of Neptune on Pluto's orbit provides an example of how interactions between different planets can shape the trajectories of smaller bodies over time. Future studies on the orbit of Pluto and the potential for a collision with Neptune could help refine our understanding of planetary dynamics and enhance our predictions regarding the behavior of celestial bodies. As we continue to explore the mysteries of Pluto and the farthest reaches of the solar system, we may uncover new insights into the fundamental forces that govern our universe. A collision between Pluto and Neptune, though unlikely, would be a monumental event that could provide invaluable opportunities for scientific discovery. Whether or not it happens, the investigation of Pluto's orbit and its relationship with Neptune will continue to inspire astronomers and physicists as they strive to unlock the secrets of our cosmic community.